Hi class. Okay, so today we're just going to go over homework 7. And problem 1 was to come up with a formula for the maximum voltage a solar cell can deliver. And you know how to do that because I told you that I, for the diode, or when I add IL, the solar cell, meaning illuminated diode. All right, I'll write it out first. Okay, I'll include the -1 first, and then we're going to get rid of that. Let me put in gap. Okay, so this is the current for a dark diode before we put any light on it. And now we're going to put some light on it, and as we discussed, all that means is that we add a negative current component due to the light. So if you plot this as we've done, I versus V. All right, in the dark, it looks like this. And then in the light, you just move it down IL. Okay. And in the light, what the problem is asking is what is the maximum voltage that the solar cell can deliver? And I told you the answer, because we sort of haven't really covered it in class. But the maximum voltage is the voltage for which I equals 0. And the way the way to think about that is that, for example, if you have a load on it that's asking for a certain amount of voltage, and you increase the voltage requirement, as you get close to this value, the current that the solar cell can deliver to the load starts going down. And finally, when you get to this point, imagine it's a battery. So let's draw our solar cell. Okay, here's our solar cell. And this is VF plus minus. And so there's our solar panel, and we want to charge a battery, let's say. Battery. So, I mean, you can imagine, you can buy these things. You have a little solar panel that you can hook up to your cell phone to charge the battery. And importantly, when the solar cell is illuminated, the current is in this direction. All right. The thing you have to realize about these current voltage diagrams is that if this is I diode, right, it is defined going into the diode, right? Because of course, in the dark, right, as I increase the forward bias voltage, I increase the current in that direction. And the fact that the solar cell causes this current referenced in that direction to go negative means that the actual absolute value of the current is going in that direction, and we can charge the battery. So it's absolutely a requirement that I be able to, that the solar cell, the illuminated diode, has the characteristic that it can deliver a negative current for a positive voltage across it. Okay, and so imagine, this is V battery. Okay, and everything's working fine. I'm delivering current in that direction because it's the opposite of that direction, and I'm charging the battery. And now imagine V battery keeps going up here. And so if it goes up to here, okay, I can deliver that much current. All right, less. Okay, and then finally when it gets to here, that's the maximum battery I can charge because, I'm delivering zero current, but that's clearly the maximum. If the battery voltage exceeds that, then the current starts going in the other direction and I'm not charging the battery. In fact, the battery is charging the solar cell in a sense, or driving the solar cell. So this voltage is the maximum voltage that the solar cell can deliver. And we term that VOC. In the problem, I didn't say why we call it VOC. OC stands for open circuit, which is basically meaning if, okay, think about it. If I have the solar cell, and imagine I just hook it up to a voltmeter. And it's illuminated. Okay, a voltmeter doesn't draw any current, right? It just measures the open circuit voltage of the load, and that would be VF. So if you took any diode, well, I mean, if you took a solar cell and you hold it out in the light and you hooked up a voltmeter to it, it would read this voltage because that's the open circuit voltage, which is what a voltmeter measures. Okay, so anyway, let's get back to the equation. So you were asked to calculate VOC, and I told you that you could approximate that for this purposes of the problem, that I is approximately equal to e to the minus e gap, I naught, over kT. Times e to the EVF over kT minus IL, meaning I neglected the 1. And the reason I can do that is because I want to determine this voltage. And clearly, from what you've learned, VOC is going to be some number, between half a volt and a volt. It's much bigger than kT. And so this dominates over that, and you can take the 1 away. And basically, what you're calculating is the voltage at which I equals 0. So you write down 0 is equal to I naught e to the, now put them together, all right, and now let's solve. So basically I can write down by putting the IL on the other side. I could write down IL over I naught equal to e to the minus e gap minus e VOC over kT. Now I could write that down. Here it's helpful to use your understanding of things to write it down better, because you see, if I write it down this way, okay, that is e to the minus some negative quantity, and so what I'm going to do here is I'm just going to flip these things. And get rid of that minus sign. All right, so what I've done there is I've just made things a little bit easier to think about, because now this ratio is e to a positive quantity. And so when I take the logarithm of both sides, All right, that logarithm is now a positive quantity. And I can put the KT on the other side. And then I can solve for VOC. And that over there, you get over E minus KT over E logarithm of I naught over IL. And that's the answer. Hopefully by now you've gotten used to the idea that if you go from, for example, KT in electron volts, to convert from energy, you divide energy by electronic charge. And so if KT is 0.026 electron volts, when you divide it by E, it's 0.026 volts. And so you get the idea here. Now, some of you, I think, I looked at a few papers, plugged in numbers here, but really this is all I was asking for. But I wanted you to tell me something about I naught over IL. And you can go back to here to get what I was trying to get you to answer. Because, as I've always said, EVOC never exceeds E gap. All right, so this is E to some positive number, right? E to a positive number has to be bigger than 1. All right, E to the 0 is 1, E to the 1 is 2.7, E to the 2, etc. You get the idea. E to some positive number has to be bigger than 1. So what I wanted you to tell me was that I naught over IL has to be bigger than 1 in this analysis. So because it's bigger than 1, the logarithm of something bigger than 1 is a positive number, and so VOC goes down with temperature. All right. Since I naught over IL is bigger than 1, VOC goes down as temperature goes up. Now remember, I already showed you that in the lecture, because if I increase temperature, I goes up. Right? This is like 300 Kelvin, and this is like 400 Kelvin. And so as temperature goes up, the current at a given voltage has to go up. And since the curve is shaped like that, that means the curve moves to the left. So as temperature goes up, the voltage goes down, or the voltage at a certain current. And since this curve is simply that displaced, the same thing happens here. All right, as temperature goes up, VOC goes down. And so in this formula, proper use of this formula requires understanding that this ratio has to be bigger than 1. Okay. Okay, so that's problem 1, and you can see the solution is pretty simple. The ramifications, by the way, that VOC goes down with temperature is that as a solar panel gets hotter, it can deliver less power. And you can sort of see that because power, remember, power is current times voltage, so I can deliver a certain amount of current, right, at a lower voltage, and so the overall power delivery goes down. So you would like your solar panel to not get hot, which is, of course, I can't do. But anyway, that's another course, how that may or may not be dealt with. All right, problem 2. So problem 2 is to calculate I naught. All right, so so we want to calculate I naught. Okay, what is I naught? And I gave you certain values for, so this was, kind of a plug in the numbers, but first you had to derive the formula for I naught. Now, let's just start now. So what I've sort of taught you is that, when approaching a diode problem, namely trying to figure out the current, let's start with J here. So remember, okay, J is E times the flux, so that's E times, for the whole, it's dP dx. All right? And, I'll put off to the side here. Well, let me just write it down because, it's almost easier just to think about it this way. Oh, forget that diffusion. Okay, ED dP dx. So, what is dP dx? Well, okay, I'm not even going to draw it because you want to almost hold it in your memory at this point. Remember the injected carrier density right next to the junction goes as the equilibrium carrier density times e to the EVF over kT. Okay, and it goes down to Pn0. All right, and what I've explained to you is that you can kind of think of it that it, even though it's going in an exponential decline, you can think about it as kind of this straight line where where dP is that and dx is L. And you can get the same answer by actually writing down P of x and taking the derivative, but it's almost kind of easier just to start at this point. All right, so basically that's it, and so we can write down then that I is A times J, and we'll include both components. So let's do E. Now I'm going to write down both components, but I set up the problem so you don't need to do that. BH Pn0 over LH plus DE and P0 over LE times E to the EVF over KT minus 1. All right, and so we recovered our diode equation. Now, you'll notice that I naught over here was written for a slightly different form. I have to have it in the form where it shows this. Okay, so we have to do a little bit of reduction here. I mean, you know how, your best friend in the whole wide world, right? Pn0, okay, I'll write it out. Pn0 is Ni squared over N equilibrium. Okay, basically that's the electron concentration far from the junction, and write down that's approximately equal to Ni squared over N D, the donor concentration, because most of the time, if not always in this class, we can approximate that N is equal to ND out in equilibrium. So let's, and similarly, NP0 is Ni squared over Na. And Ni squared is equal to N times P in equilibrium. Right? And what is your best friend in the whole wide world in this course? N is NC e to the negative EC minus EF over KT, and P is NV e to the negative EF minus EV over KT, your best friends in the whole wide world, right? And so this becomes NCNV e to the minus E gap over KT, because of course E gap is equal to EC minus EV. So, I mean, going through this, it just, be second nature by now. So then we can write I, forgot my A here, equal to E, A. Now what I'm going to do is I'm going to well, just write down DH over LH PN0 ND plus DE over LE NA times Ni squared, and Na squared is NC NV e to the minus E gap over KT times E to the EVF over KT minus 1. And now we've gotten in the form where this is I naught, because we have our E to the minus E gap thing here. All right, now at this point you have to kind of think things through a little bit, because I didn't give you NC and NV. And I did give you Ni, and I sort of did that on purpose, because well, let's just do it. Well, okay, so the reason why is because I can never, you can't really look up. It's hard to look up, or, because it's not published. NC and NV, the effective density of states, I don't even remember what the number is. And but what I gave you in the problem was I gave you Ni. I gave you that Ni is 10 to the 10th. All right. Because that's a number. You could just Google an intrinsic carrier density for silicon, and it'll tell you what it is. So you have to do a little bit of manipulation here. Okay, I naught is equal to EA DH over LH ND plus DE over LE NA times NC NV. But, okay, all right, go back here. You have to use this formula to plug in for NC. So it's kind of like you're going backwards a little bit. But NC NV is Ni squared times E to the E gap. So that's I naught in terms of Ni. And it's sort of circular because, when you plugged in for P and 0, you could have just seen that directly when you did the plug-in. But, okay, there it is kind of sort of formally, mathematically. So you had to make that switch because you didn't know these. Okay, but you know that that's equal to Ni squared times E to the plus E gap over KT. Okay, and we can collect terms because I said the diffusion coefficients and the doping and everything is the same. Basically, this is 2 EA B L N and I squared e to the E gap over KT. Because N is the same for both. And remember, L is the square root of d tau. So I naught is then equal to 2EA d square root of d tau n and I squared e to the E gap over KT. Okay, it's just sort of bringing things together. 2EA n I squared over n. Then collecting everything. 2EA n I squared over n. Yep. Times the square root of d over tau times e to the E gap over KT. And I'm just making sure I'm still in focus here. All right, so I naught plugging in. So it's 1.6 times 10 to the minus 19. I told you the area was 1 centimeter squared. All right, now in principle, in principle, as a general rule, you should always convert to MKS before you plug in numbers, but this is a case where you don't have to do that. Because D, I gave you in centimeters squared per second. So I can put everything in terms of centimeters. So Ni squared is 10 to the 10 squared. The way to think about this is that D is area per time, and so the square root is distance. And so when I have, if I have area in centimeters squared, and I have Ni squared in 1 over centimeter cubed, and N in 1 over centimeter squared, and this in centimeter, then, when I take the square root, then all the centimeters cancel out, and I get Coulomb for time. Actually, it's a good exercise. I won't do it here, but when I hand out the answer, go through it and make sure that you got that the units are current. All right, N I told you was 10 to the 17. All right, and then that's the square root of D, I said was 10 centimeters squared per second, and I said tau was 10 to the minus 7 seconds. And we'll do that in a minute. Okay, and so when you work all that out, you get 3.2. That's 2 times 1.6. If you do all these 10s, you get a 10 to the minus 13. But then I got to multiply times E. I gave E gap as 1 EV divided by 0.026. And so I naught, when you take that exponent and multiply it, works out to 16,200 amps. So pretty big current. And so I naught here is that, and that's the answer. Okay. Let's see. So let me see how I want to organize things here. Let's leave problem 2 up, and what I'm going to do is I'm going to erase this. Okay, I want you to go over the solution, make sure you can do it, and I'm going to put, for problem 2, I naught equals 16,200 amps. Okay. And then let's erase this. And do problem 3. So problem 3 was, I said that, okay, you have your 1 by 1 centimeter device. Remember, that's the same value. So A is equal to 1 square centimeter. And I told you that full sunlight has a power of watts per centimeter squared. All right, and the problem is set up for you to think it through. Okay, so I said every photon makes a charge carrier that contributes to photocurrent. All right. Now here students, may get confused about a factor of 2, which I don't want you to be confused about. Okay, in the diode, right? We make an electron hole. Light comes in and makes an electron hole pair, right? Okay, and the hole moves one way and the electron moves the other. So the reason why I said every photon makes a single charge carrier that contributes to photocurrent is because if you look at any plane in the device, only one of the charge carriers is contributing to current at that point. Okay, so I just wanted to clarify or make clear that every photon makes a single moving charge carrier at any point in the device. Okay, and so you're supposed to calculate photocurrent, IL. So the way you do that is you have to calculate the photons per second. All right, so that's equal to the joules per second. Well, okay, so yeah, let's do it this way. Joules per second. That's the power in the light. See, we're basically calculating the photons per second in sunlight, divided by the joules per photon. All right. So the joules per second, that's watts, right? That's 0.001. Now, what are the joules per photon? Well, I gave you the EV per photon. Okay, so it's the joules per photon, or it's the EV per photon times the joules per EV. Right, so that's 0.001 times, okay, EV per photon I gave you is 2. The joules per EV, that's just the electronic charge, remember? That's how you convert from eV. So that's 1.6 times 10 to the minus 19. Okay, and I'm just going to leave it that way, 0.0005 over 1.6 times 10 to the minus 19. And I'm going to leave it that way for a reason. I mean, you could work it out and give you the number of photons per second if you wanted to. But the point is that the current, right, I is the charge per second, which is the electrons per second times the charge per electron, which I said the electrons per second is the photons per second. Okay, the charge per electron is 1.6 times 10 to the minus 19 coulombs. And so, you know, if you just leave it in that form, you see that the 1.6 times 10 to the minus 19 cancels out. And so it's 0.0005 amps. Okay, so that's the answer, 0.005 amps. All right, now in the problem I said, okay, that's the answer, that's what you need to do for full credit. But I wanted you to sort of then put all the three problems together and sort of convince yourself that this all makes sense. And so what I'm going to do is I'm going to calculate VOC at 300 Kelvin. All right, so that's equal, and I said for a band gap of 1 eV somewhere, I think. Well, I mean, I said that earlier in these problems. So 1 EV means that's 1 volt minus 0.026 times the logarithm of I naught, 16200, over 0.0005. And if you work that out, that's 0.55 volts. So for full sunlight, VOC is equal to 0.55 volts, which is about right. You know, I sort of made up the parameters of the problems, but you know, that's not a very good solar cell, giving you a VOC of 0.55 volts at room temperature. But I mean, a good a good solar cell, for a good solar cell, that number would be closer to maybe 0.7 volts. Meaning, if you took a solar panel and well, not a solar panel, a single solar cell. Maybe after we do MOSFETs, we'll circle back and talk about solar panels versus solar cells and stuff like that. But for a solar cell, if you hold it out in the full sunlight, you might get closer to 0.7 volts. And you can sort of see, although I erased it, the things that might make you able to get a higher VOC. In particular, you basically want I naught to be small, okay? And so if you go back to the formula which I erased, you want tau to be longer, right? Which makes sense because if tau is longer, your carriers aren't recombining, and everything is making it through the junction and contributing to overall power. Okay, so that's homework 7, and we'll discuss it in the chat class tomorrow, and then go from there. Okay, thanks.